Hey, Dr. Clark here, coming back at you with another main idea video, this time looking at the properties of the Laplace transform. So the first property we want to talk about is how multiplication by e to the at in the time domain becomes translation in the frequency domain. So if you have some basic function like sine omega t, we know that the Laplace transform of that is omega over s squared plus omega squared. What's the Laplace transform of, say, e to the at times sine omega t? Well, really, you just take the standard form of sine over here and replace s with s minus a, which really means you're just sliding that function over in frequency space. So essentially, multiplication by e to the at in time space creates a translation in the frequency space. And you see the same thing with cosine, right? S is essentially replaced with s minus a here. And the same thing with t to the n. So if you have n factorial over s to the n plus 1, when you multiply by e to the at in time domain, you're going to get n factorial over s minus a to the t, or to the n minus 1. So it's just sliding that function over in the frequency domain. All right, and we're going to use this in solving differential equations because anytime the solution would come from a function like this, what you'll see on right-hand side is something that looks like this, and then you just need to recognize that as, oh, that's basically the sine function, but shifted by e to the at in time domain, so it's shifting by s minus a in frequency. Okay? This is a general principle. It's not just true for those three functions I showed you. It's generally true that e to the at times f of t under the Laplace transform will give you s replaced with s minus a inside of the standard Laplace transform of little f. So if L of little f is cap f here, if that's the standard function like we have here with, you know, sine becoming omega over s squared plus omega squared, then what you're going to get is that standard function, but s replaced with s minus a, and then you can do the inverse as well. If you see this on right-hand side, when you Laplace inverse it back, it's going to come from an e to the at times f of t. Okay, so that's the first idea. And then the second idea we're going to talk about is using these unit step functions. One of the main nice things about Laplace transform is it lets us solve differential equations where the forcing term is messier than what we've handled before in this class. And to do that, we're going to use something called the unit step function, which we call ut minus a. If a is 0, then this basically just is 0 and then starts at 1, starting at t equals 0. If you do ut minus a, it just shifts that over to 0 up until the number a, and then it becomes 1 after that. So it's the unit step function. And it's a Heaviside-Type function, so sometimes I call this a Heaviside function. And if you wanted a step function that went from, say, 0 to 2, well, then you could just multiply this by 2, right, and you'll get 0 to 2. So the unit step function is 1 unit, but you can make it however many units you want. Another thing you can do is you can multiply this by other functions, like, say, t squared or something, and then that t squared will be 0 until it turns on, right? So it's useful to sort of turn on or turn off functions by making it 0 or 1. Okay, and here's some examples of us doing that. How would you take this piecewise defined function and write it more simply and compactly using these Heaviside or unit step functions like this? Okay, well, f of t starts at 0 from 0 to 2, and then at t equals 2, it becomes 3. So we're going to need a 3 unit step function starting at 2. And then at 5, it's going to jump up from 3 to 10. So we're already going to be at 3. We need to get to 10, so we need to add another 7 unit step function. So check this out. If we take this piecewise defined function, we can write it very compactly as 3 unit step functions starting at 2, and then 7 more unit step functions starting at 5, so that at 5 you got 3 plus 7 is 10, but between 2 and 5 this one is still 0, so it's just 3. Prior to 2 they're both turned off, and so you just get 0. Okay, so think of this u as a function that's off until it's on, and it's on at the number that it gives you inside of that bracket, so at t equals 2 basically. All right, what do we have here for g of t? We start off with the 3t function from 0 to 2, And then at t equals 2, we're going to need to turn on the 6 function and turn off the t function. Okay, so watch this. We've got 3t, ut, so at t equals 0, that 3t turns on. So it's going to go up. And then starting at t equals 2, we need to turn off the 3t function. Well, how do you turn it off? Well, you just subtract 3t, so that starting at 2, both of these are 1 and 1, and then you get 3t minus 3t is 0. So that's gone. But then we need to be at 6, so we turn on a 6 function starting at 2. Okay, so you get the 3t function turns on at 0, the 3t function turns off at 2, and then the 6 function turns on at 2. And here's h of t. We're starting at 0 from 0 to 1, so we'll just need a 0 function up until 1. Starting at 1, we need a 4, so we'll turn on a 4, and then starting at 3, we need a 0, so we'll turn that 4 back off. So we really should just have 4 ut minus 1, turn it on at 1, and then 4 ut minus 3 with a negative, so it subtracts 4. So between 1 and 3, we just have this 4. After 3, we have 4 minus 4 is 0, and before 1, we'll have 0 because there's nothing there. Okay, so you can use these unit step functions to compactly write some piecewise functions in this nice way. And then the next step is to just learn how do you take Laplace transforms of these kinds of unit step functions so that we can actually use them to solve differential equations. Okay, and that's called the second translation theorem. So if you have some basic function like sine or cosine or whatever it is, and you know the Laplace transform of that basic function, okay? Then what you're going to do is you're going to say, well, let's turn on that basic function starting at a number a and shift that basic function so that it basically starts at that number a. And then if you take the Laplace transform of that, what it's going to look like is just the Laplace transform of the basics function multiplied by e to the minus as. Okay? So it is not the case that the Laplace transform of a product is the product of the Laplace transforms. That's not really what's happening here. In fact, that's not even true in general. But it is true that if you have this unit step function times a shifted function, that what you get is the regular function and then multiplied by e to the minus as. So that's kind of just this weird property, but we'll see it in action in a minute. What's often going to happen is you're going to see on right-hand side when you're solving differential equations something of this form, and then you're going to know, oh, that must have come from a shifted basic function turned on at a particular number. And the way this comes about is, again, from the integral definition of the Laplace transform. It has to do with when if you have some function that's turning on, well, that's kind of like doing a change of variables in the integral, which shifts the integral over, and then you get this minus e to the minus as term popping out. So you can prove this if you want to sort of go through all the details. It's a bunch of change of variables in the integral, but it can be done. Let's see it in action with an example here. So they want to just find the Laplace transform of this f of t function, where f of t is 0 up to 3, and then t minus 3 squared after t equals 3. So if you graph this, it looks like 0, and then it looks like a t squared function, but the t squared function starts at 3. Okay, so this is getting back to this idea. I know what the Laplace transform of t squared looks like, but I've shifted that t squared over and started it at t equals 3, so I should be looking for something of this form here. Okay, so let's see how you would solve this. So the first thing, you would write f of t using our standard notation, which is just to say it's t minus 3 squared turned on at t equals 3. It's 0 before that, so a unit step function exactly does that for us. And then I just need to do L of f using this formula. Well, the shift is of 3 units, so I should have an e to the minus 3s times the Laplace transform of the basic function, which is the t squared function. Right? This is a type t squared function, and I know that the Laplace of that is 2 over s cubed. So the Laplace of this is e to the minus 3s 2 over s cubed. All right, and that's all there is to it. So if you wanted to have some forcing term that was 0 for a while and then turned on and looked like a t squared, basically, then this is how you could Laplace that. All right. And then we've got one more, just kind of a basic example here. What if you had this on right-hand side and you needed to take the Laplace inverse of that? So say you're solving some differential equation, you've got right-hand side, and you need to bring that back. How would you do that? Well, first I would rewrite this just kind of so it looks in the right form. Well, it looks like e to the minus pi s times s over s squared plus 4. So when I see that, I'm seeing, oh, this looks kind of like cosine, but it's multiplied by e to the minus pi s. So if I go back, I'm seeing it's a basic function, right? Looks like the Laplace of cosine, but then multiplied by that. So when I come back, I should be seeing a shifted version of cosine turned on at that number. Okay, so let's take a look here. So first we're going to write it that way. We're going to note that the Laplace transform of cosine of 2t would be s over s squared plus 4. So we got the 4, so that's generating the 2 there. And then we should just end up shifting it over by pi units and turning it on at that point. So the Laplace inverse of that would be ut minus pi. So shift by pi and turn it on at that point, and then shift the cosine function by pi. So you're going to essentially replace t with t minus pi. So that's how you would solve that one. Okay, so the next step would be basically to give yourself a differential equation where right-hand side includes some of these shifted terms with e to the minus as in them, and then figure out how to bring those back and generate solutions to differential equations. So we'll see some of that in the next video, but until then, hopefully you're getting the main idea of what's going on, the first and second translation theorem, and we'll see it in action with some examples later.